Ever wondered why a conveyor doesn't start the instant you press the button, there's a few seconds delay first? Or why a fan keeps running for a while after you tell it to stop? That's a timer instruction doing its job. Today we cover the three you'll actually use: TON, TOF, and RTO. Not everything on a plant should happen instantly. A downstream conveyor needs to confirm it's already running before an upstream feeder dumps material onto it. A cooling fan needs to keep running for a few minutes after a motor stops, to pull heat away. A fault shouldn't trip the plant on a half-second glitch, it should wait to see if the condition is still there a few seconds later. All of that is timer logic. Let's go through the three main types. TON, timer on delay, is the one you'll use most. Here's how it works. As long as the input condition is true, the timer counts up from 0 toward its preset value. The instant the accumulated time reaches the preset, the timer's done bit turns on, and that's usually what drives your output. But here's the important part: if the input goes false before the timer reaches preset, the accumulated time resets straight back to 0. No partial credit. It has to run the full preset, uninterrupted, to complete. Real example: a downstream conveyor confirms, running, feedback. You wire that feedback into a TON with a 5-second preset before allowing the upstream feeder to start. That gives the conveyor belt time to actually get up to speed and stabilize before material starts landing on it. TOF, timer off delay, works the opposite way. The output turns on immediately when the input goes true, no delay there. But when the input goes false, the output stays on for the preset time before finally dropping out. This is exactly your cooling fan example. Input is motor running. Output is fan on. The instant the motor starts, the fan starts too, no delay needed there. But the moment the motor stops, you don't want the fan to stop with it. You want it to keep running for, say, 3 more minutes to carry residual heat away. That delayed dropout is TOF. RTO, retentive timer on, behaves like TON in one way: it counts up while the input is true. But if the input goes false, the accumulated value doesn't reset to 0, it holds right where it was. When the input goes true again, it picks up counting from that same point, not from scratch. Because of that, an RTO needs a separate reset instruction, otherwise that accumulated time could sit there indefinitely, even across power cycles on some platforms. Where you'd actually use this: tracking total run time toward a maintenance interval, even with the equipment starting and stopping throughout a shift. Or accumulating total, fault present, time across several short trips, so you catch a pattern of nuisance faults instead of losing that history every time the fault clears. Let's put all three side by side, reacting to the exact same input pattern. TON only completes if the input stays true for the full preset, and resets the moment it drops. TOF turns on instantly but delays turning off. RTO keeps its memory across multiple separate on periods until you reset it manually. Same basic idea, count time, but three very different behaviors, and picking the wrong one is a common source of logic bugs for junior programmers. Quick recap: TON delays turning something on, and resets if interrupted. TOF delays turning something off, letting it coast down gracefully. RTO remembers accumulated time across interruptions until it's manually reset. Once you know which behavior you need, picking the right timer instruction becomes automatic. Next video, we'll cover counters, CTU and CTD, and a batch counting example you'll recognize from bag counting or cycle counting on the plant. Subscribe so you don't miss it.